Hi, in this tutorial I'm going to talk about the Octomap and the concept, the idea, and the ideas behind it, and how the way to store the data in a tree. And then I'm going to go through the formula that has been introduced in the related publication, and I will walk through all the formula step by step. So first, the idea behind the Octomap. I will imagine you have a map like this, and you want to store the data. So this is your occupied area, and this is your free area. So one common approach is to discretize the space to a grid n by n, and then we store the data in a matrix of n by n, which is not a very sophisticated approach, and it gonna take up huge space in the memory. Well, in the Octomap, imagine you have this map again, and you want to store it. We will divide the space into 4 squares like this, and this is number 1, number 2, number 3, number 4. And we start building a tree with 4 nodes, which are not responsible for all of these squares. And we will see, we will have a look on the squares, which squares are occupied and which one is free. And if you can see, number 3 is almost occupied. So number 1, 2, 3. So for this node, we won't continue any further, and we will label it as occupied. But for number 4, and also number 2, you can see it's totally free, so we won't continue. But you can see for number 4 and number 1, they are partially occupied. So we continue with number 4. Again, we divide it into 4 space, and we call them again 1, 2, 3, 4. And as you can see, number 3 is totally occupied. Number 1 and number 2 and number 4 are partially. So again, we continue for these 4. We divide it again. And as you can see, again, some of them are occupied and some of them are free. So for those that are free, we continue, that are half free, half occupied, we will continue this division until we reach a certain level. So as you can see, we will continue this tree, and we will have some subtree here, which for some of the lifts we stop, and for some of them we continue. And instead of storing the data in an n by a matrix, we store it in a much dense tree. As you can see, we save up a lot of space with this tree. Of course, this wasn't 2D. When you work with a real map, you usually work with 3D data. So instead of square, here you have cuboid, and it's exactly the same concept, but you have, instead of 4, you have 8 child for every node, and you have to divide everything to a cuboid. Okay, in the second part of the video, I want to go through the probability model and the mass, and I want to crack down the formula that has been used for updating each node in the tree. So the probability of leaf or node n to be occupied after t time measurement from time 1 to time t we denote it by this symbol. So this means if the knot T is, knot N is occupied after T time measurement, and it's so occupied, and it's free, well, obviously the complement probability mean is free, so it's denoted with PC. There's a C, small c here, complement. So the probability that knot N is free after T time measurement, which is 1 minus . And we also, well, we obviously know the Bayes rule. And we also know the Bayes rule and the joint probability. This means probability of A given B and C is equal to this term. Okay, now if I write down probability of C, PC, that means complement probability, or 1 minus the probability, like this term here, of knot N given T time measurement. And instead of writing it like this, I will write it like this. T minus 1 to 1, and the measurement of time T. So it's just the same it's the same term. It just I just separate the last measurement from it, but it's exactly the same term. And if I put this guy instead of A, this guy C, and this guy B, so you can see we have exactly this formula here with this term. And if I just use the superposition and just use the Z and N instead of A, B, and C, I will have this term, probably C. Okay. Now I can do the same for, that was for complement probability. I can do the same for this term here, which exactly give me the same term, but instead of this C here, it will give me the probability, not complement probability. So I will have probability of N, probability of not N to be free after T time measurement. Okay, and if I divide these two terms over each other, this over this guy and this over this guy, I will have probability of n to be occupied after t time measurement. Okay, so we ended up to this formula, and we know that the probability of a measurement for naught is only dependent on the measurement time t. It means I'll use a blue one. Probability of measurement at time t given previous measurements, that time minus one and n. This only dependent on the naught, so it doesn't depend on the previous measurements. Makes sense when you sensing a knot. It doesn't, the measurement at that time, it's only dependent on the time t, not anything else. So we can make this term a little bit, these two terms simple, and we will write it like this. And here I'm just using the, for this term, I'm just writing it like this term. Probability of complement is always equal to 1 minus the probability. So 1 minus n. Minus 1, 2, 1. And for this part, I'm using this assumption. Multiple by probability of C. Okay, so yeah, this is very simple. The probability of the measurement at time t, it's only dependent on the measurement only depended on the state, doesn't depended on the previous measurement. When you sensing a knot, for instance, in your scene, it's only dependent on what is here, no matter what has been sensed before. Okay, so I will use Bayes rule here for these two terms. I will use this Bayes rule here for this term. I will keep this one. So this will give me this term 1 minus probability of n. So I just apply Bayes rule and it will give me probability of n given measured time t multiplied by Okay, so now I can get rid of this term, and I will just make it a bit more simple, and I will rewrite it like this: 1 minus so this guy goes to the top, and this guy will go down, and instead of writing it probability of complement, we'll write it 1 minus probability of n. We'll get rid of these two terms, and we have this guy here, and this guy here as well. Again, we write it 1 minus probability of n given z. Okay, so if I will call this term as I don't know, let's call this guy x. We started with this guy, if you remember. We started from this guy, and then we make it more, we use the Bayes rule, and then this guy, and this term is equal to, we will call it x. So let me just write the rest. I will write it down here for you. What is? And again, here you can see we have the probability of complement. We just write it down 1 minus probability of n. Okay. And I will just decompose this term. So 1 over this probability minus 1. So just divide this term. So we have minus 1 plus 1 over probability of n, sorry, zt, or in another word, we can just put the x on the other side and make it upside down, which gives us probability of not n to be occupied after t time measurement from time 1 to time t, 1 over x plus 1, or x plus 1 minus power minus 1. Okay, so if you look at the paper, so this is formula number 1, which has been introduced in the paper. As you can see here, we have lots of multiplications, and it's computationally it's easier to do the summation instead of multiplication. And you know that from the logarithm function. If you use a logarithm function, you can always turn the multiplication into summation. And they have introduced logs out function, which which take the logarithm of anything over its complement. So for the n, it will be p of n over 1 minus p of n. And so they apply it to this term. I mean, what they put in each node is not as probability. They put the log of probability, and you can easily going back and forth. So every time you have a new measurement, instead of doing this 3 times multiplication, you just do a simple summation, and you put the logarithm of the probability. And they will have formula number 2. If you look at these 3 terms, this guy is a probability of n over its complement. And at the beginning, we don't know if one node is free or occupied. So the chance is 1 over 2. And this term will turn to 1. And the logarithm of 1 is 0. So it will make it to 0. So we have only 2 summation. If we have only 2 terms, so L of n given okay, in the next part of the paper, we have the sensor model. Means how much we trust our sensors. Will the sensor that have used is a SICK laser scanner, and the beam will heat space. If there is something here, if it's free, it will go through that, and if there is an obstacle here, it will the ray will hit back, and the sensor will notice that. But there is always uncertainty about that, which means there might be something and the laser beam doesn't hit it. Another way around, there might be nothing here, but the our laser scanner might think that it already hit something and there's something there. So there is always uncertainty. And for the laser scanner they have used, they consider the probability of 0.7 for the case there is something and the laser beam has hit something, and probability of 0.4 for the case that is free, and the sensor tells us, okay, this this space is free. And as I said in the earlier section, we don't put these numbers inside of each node, but we put the logarithm of p over 1 minus p, which in this case we put the probability of 0.7 over 1 minus 0.7, which gives us 0.84. And for occupied area, and for the free area, it will give us 0.4 over 1 minus 0.4 will give us minus 0.4. So if you look at the code, which I will put it in another video, how to use the Octomap library, you will see these numbers 0.4, minus 0.4 and 0.84 for the occupied and free area. The other thing that is discussed in the paper that okay, if your scanner starts scanning and after I don't know, t-time measurement, it's find an obstacle, so it needs another and when we move that obstacle, we have to again observe that particular cell t times, so we can see that's a free area according to our updated formula, because every time we were accumulating the probability one on top of each other. And this eventually, this is good for a stationary scene where nothing is moving. So if you put a scanner there and it starts scanning, it'll tell us, okay, this is occupied, and this gives us a higher probability number. But if you work in a dynamic environment and I don't know, there's a person standing in front of your scanner for a couple of seconds and then he or she moves, then the scanner with this model, the scanner will say, okay, it's a free area, but the model tells us that, okay, I have to accumulate it for another t time so I can see it's free, which is pretty bad. So we have to put some clamping policy that we don't accumulate it until infinity, and we should cut it somewhere. And the formula number 4 is telling us this. The probability of not n to be occupied after t-time measurement, of course the logarithm I told you earlier, or the log's odd function, is equal to maximum of, that's a big guy, I have to, okay, so this is the mean, and this is the max function. So what does it tell us? It tells us that, okay, if we have two terms here, L max and L mean. There are again some arbitrary numbers, again like just 0.7 and 0.4 that they have introduced. You can change your code. This is for the SIG laser scanner that they have used, and here they again put two numbers. For minimum they put L of minimum, I guess -2, and L of maximum is 3.5. Which again, it's coming from these two numbers, 12 and 97%. If you get the ln logarithm of yeah, for -2, if you get the logarithm of 0.12 or 1 minus 0.12, you will get -2, and if you get the logarithm of 97 or 1 minus 0.97, you will get this number. So this is a point, this is the numbers that they or they get the 97 and 12. In the paper they explain they empirically get these numbers. Okay, so what does this clamping does for us? As you can see here, if we start observing the state to be occupied, and we just accumulating the data, the numbers, and you can see it will tell, okay, I will get the minimum of these two. If we getting bigger than 97, probably to 97% or 3.5, we will get the minimum always. So it always guaranteed that we never goes more than 97 or 3.5. And other way around, if we just scan somewhere and we see it's free, and it doesn't go smaller than 12%. If you get a small value, you can see this -2 comes out, but it could never be less than -2, because here again we get the maximum of -2 and the number which comes from here. Consequently, we could never goes higher and lower than these two numbers, which help us for a dynamic environment after a couple of measurements. If something changed, we could easily realize that. Of course, if you're toying around with these two numbers, you can quickly realize that, but it increased the faulty measurement, because you might quickly make a decision which is not very good. So they have found these numbers, I think empirically. It's if you found these numbers in the paper, that's where they come from, -2 and 3.5 from this equation. Thank you.